Hello everyone. Welcome back to my YouTube channel Chemical Adda. In today's video, we are going to solve an example related to drying under constant drying conditions. So in this video, we will understand how we can calculate the time required to dry material under constant drying condition. But before we solve the example, let's first understand what is given in the example. So, in the example, we are given that all moisture contents are on a wet basis. This means that we are given that moisture content on wet basis, which is denoted by small x. Then given that slabs of paper pulp 100 cm into 100 cm into 1.5 cm is to be dried under constant drying conditions from 67% to 30% moisture. So, in this example, drying occurs from a slab of paper pulp under constant drying conditions. Then we are given that the area of the slab of paper pulp, that is A, is equal to 100 into 100 into 1.5 is equal to 2 meters square. Then we also given that the initial moisture content, which is denoted by small x1, is equal to 0.67. And the final moisture content, which is denoted by small x2, is equal to 0.30. Then, in the example given, the equilibrium moisture for the material is 0.5%. Hence, we are given equilibrium moisture content, that is small x star, is equal to 0.05. Next, in the example given, if the critical moisture content is 60% and the rate of drying at the critical point is 1.5 kilograms per meter square hour, which means that we are given critical moisture content, which is denoted by small xc, is equal to 0.60. And constant rate of drying, which is denoted by Rc, is equal to 1.5 kilograms per meter square hour. Next, in this example, we have to calculate the drying time. Which means that we have to calculate the time required to dry slabs of paper pulp from 67% to 30% moisture content. Then again, in the example we have given, the dry weight of each slab is 2.5 kg. Hence, we can take the dry weight of the slab, which is denoted by W dash, is equal to 2.5 kg. Alright, now let's move on and solve the example step by step. So in this example, we are given all moisture content on a wet basis. That's why, first let's convert all moisture content on a dry basis. Therefore, first let's calculate initial moisture content on a dry basis, which is denoted by capital X1, and the formula for it is capital X1 is equal to small x1 divided by 1 minus small x1, where small x1 is the initial moisture content on a wet basis, which is already given as 0.67. So, after putting the value of x1 and solving it, we get capital X1 is equal to 2.03. Then, let's calculate the final moisture content of the slab on a dry basis, which is denoted by capital X2. So the formula for capital X2 is capital X2 is equal to small x2 divided by 1 minus x2, where small x2 is the final moisture content on a wet basis, which is already given as 0.30. So after putting the value of x2 and solving it, we get capital X2 is equal to 0.428. Similarly, we can calculate equilibrium moisture content, which is denoted by capital X star. Hence, after putting the value of a small x star and solving it, we get capital X star is equal to 0.005025. In the same manner, let's calculate critical moisture content on a dry basis, which is denoted by Xc. Hence, after putting the value of small xc and solving it, we get capital Xc is equal to 1.5. Then we know that, in this example we have to calculate drying time for reducing moisture, from initial moisture x1 is equal to 2.03, to final moisture x2 is equal to 0.428. But, from the values of x1, x2, and xc we can notice that final moisture x2 is lower than the critical moisture xc. And we know that drying usually occurs in two periods. First one is constant rate period, where moisture content drops from x1 to xc, and second one is falling rate period, where moisture content drops from Xc to X2. Hence in this example, as final moisture X2 is lower than the critical moisture Xc, we can conclude that after reaching the critical moisture of 1.5, drying continues further in the falling rate period, until it reaches 0.428 final moisture content. Which means that, the total drying time covers both stages. And therefore, the total drying time of T includes time during the constant rate period, which is denoted by Tc, and time during the falling rate period, which is denoted by Tf. So, we can write T, that is, the time of drying, is equal to Tc plus Tf. Then, we know that the formula for drying time for a constant rate period and falling rate period. Hence, the formula for the time required for drying can be written as T is equal to W dash divided by ARC into X1 minus Xc plus W dash into Xc minus X star divided by ARC into ln of Xc minus X star divided by X2 minus X star. Now, if we take W dash divided by ARC common from both terms, we get T is equal to W dash divided by ARC in bracket X1 minus Xc plus Xc minus X star into ln of Xc minus X star divided by X2 minus X star, where Rc is equal to the rate of drying in a constant rate period, is equal to the area of the drying surface, W dash is equal to kilogram of dry solid, and capital X1, X2, Xc, and X star is the initial moisture, final moisture, critical moisture, and equilibrium moisture content on a dry basis respectively. Now, let's substitute the values of all the terms in the formula. So, after substituting all values, we get. After solving this, we get T is equal to 2.01 hours. Therefore, 2.01 hours will be required to dry the slab of paper pulp from 67% to 30% moisture content. So in this way, using a formula, we can easily determine the drying time. So, that's all for today's video. If you found this video helpful, don't forget to like, share, and subscribe to my YouTube channel, Chemical Adda, for more easy to understand explanations on mass transfer operations and other chemical engineering topics. Also, check the description box for notes and links to related videos, including our previous video on the basics of drying. Thanks for watching and see you in the next video.